Hello, ECA students. This week we are looking at gases. This week you will have a quiz based off this slideshow, a video lab, and a reading response. These are the topics we're going over. To save time, I'm going to continue, but if you'd like to write them down, you're welcome to pause. All right, let's get started. So we've learned about Fahrenheit and Celsius as measurements of temperature in the past, but today we will learn about temperature measured in kelvins. The first thing we need to recognize is that heat or temperature is a measurement of energy called thermal energy. This energy is determined by how fast or slow molecules are moving. When molecules move, they produce kinetic energy. Kinetic energy can be transformed into thermal energy due to the law of conservation. We can measure this thermal energy by recognizing the change in temperature. The Celsius measuring system is great when we're talking about water because 0 degrees is water's freezing point and 100 degrees is water's boiling point. But we have a lot more substances in the universe than just water, so we use Kelvin. At high degrees in kelvins, the molecules are producing incredible amounts of heat and moving very fast. At very low degrees in Kelvin, molecules are just barely moving and have very low energy states. Let's move on. So, at temperatures of 0 degrees Kelvin, we call absolute zero. Because absolutely no movement of molecules is happening and no energy is being produced. Nothing in the universe or in a lab has ever actually reached absolute zero as far as we know. One of the reasons absolute zero has never been seen is because the volume of gases would be negative, which is not possible for gases. To restate, at absolute zero, all motion of atoms stop. So everything in the universe that has mass has a state of matter. States can change based on temperature and pressure. What determines the state of matter is how tightly its particles are bound together, or how dense it is. There are 5 states of matter that you need to know. You're probably familiar with solids, liquids, and gases, but today we're going to introduce 2 more. We're going to introduce the Bose-Einstein condensates. I like to call them BECs, much easier. An example of a BEC is cold liquid helium, if you need an example. BECs are similar to solids, but with less energy. They have temperatures very close to absolute zero, but not quite there. If you would like to learn more about BECs, one of the reading response articles is about them. All right, on the other end of the spectrum, we have plasma. Plasma is actually the most common matter in the universe and makes up the stars, the sun, lightning, and I believe partly fire, but don't quote me on that. So, plasma is created when intense heat makes atoms separate into positively and negatively charged nuclei, or we can call them ions, that whiz about at very high speeds. In other words, matter gets so hot that its atoms split apart. So I'm sorry, not ions, even more broken apart than ions. Collisions between plasma from space and the gases in our atmosphere are what make the aurora lights, if you wanted to know. All right, all states of matter are fascinating in their own right, but the star of this week is gases. So gases have no fixed shape or volume and conform to the shape and volume of whatever container they're in. They are the most compressible states of matter, meaning that they have the most capacity to be flattened or reduced in size by pressure than any other state of matter. Gases will mix evenly and completely when confined to a container, creating a homogeneous solution. Remember that from last week? All right. Gases have a lower density and higher temperature than liquids and solids. We know that. We can describe gases as fluid based on their ability to flow or take shape of containers. So liquids aren't the only fluids, gases are fluid too. Sorry, I lost my spot. Okay. Mixtures of gases are always homogeneous because the molecules always thoroughly mix within the solution due to the space between the molecules. Intermolecular forces, remember those from, I think, February, have less power with gases than they do with solids and liquids. All right, so gas molecules are constantly in motion. Unlike, say, solids where they are in a crystalline structure, or sorry, a lattice structure, they vibrate, but they don't technically move around. Gas molecules move around. As they move and strike a surface, they actually push on that surface. We're going to call that push a force. We're jumping into physics here. So if we can measure the total amount of force exerted by the gas molecules, hitting the entire surface at any one instant, we would know the pressure of the gas is exerting. So we're going to call pressure, we're going to call that the force per unit area. All right. So give me 1 second. All right. Pressure is determined by an inverse relationship between force and area. The greater the area, the lower the pressure. The smaller the area, the greater the pressure. If the area is less than the force, the pressure will be high. Inversely, if the area is greater than the force, the pressure will be low. So, we consider the relationship between force and area. Which shoes do you think would have the greatest amount of pressure? Let's say the person who owns these shoes has a consistent weight, which would be our force. If the force is the same, but the surface area on the shoe changes, the pressure will change. Will the shoe with the most surface area or least surface area have the greatest amount of pressure? You think about that, and then that'll be a question on your quiz. All right. Pressure has many units, but since we only have a week to look at it, we're going to only focus on one. That's going to be atmospheres. To put atmosphere units into perspective, 1 atmosphere, or ATM, is equal to 14.8 psi, or pounds per square inch. So my bike tire needs 75 pounds per square inch of pressure, which is force divided by area, pounds per square inch. Just like the equation for pressure. 75 psi, if we convert, is equal to 5 atmospheres. Atmospheres is approximately equal to the atmospheric pressure at sea level. So gas has matter, and therefore it has mass. Our atmosphere is made up of gases, and the gravitational pull of the Earth pulls our atmosphere towards the Earth's center. Earth's atmospheric pressure is roughly 15 pounds of force per square inch at sea level. This pressure changes depending on your elevation, though. So we're up high in Denver, so the pressure will actually be less than it would be at sea level. And the deeper you go in the ocean, or the deeper you go on Earth, the higher the pressure. This pressure change depends on elevation. If we have a square foot, that would be a weight, if we have 1 square foot of gas weighing down on us, there would be a weight or a force of about a ton, or 2,000 pounds. No wonder why I have a headache. Just kidding. All right. The pressure of a gas is the result of the constant movement of the gas molecules and their collisions with the surfaces around them, and depends on the number of gas particles, the volume of the container, and the average speed of the gas particles. Gas pressure is the main reason for weather changes. The effects of gas pressure include pressure gradient, where the gas under high pressure will move to an area with low pressure. We can think of wind movements or hurricanes. And when a hurricane is active, the high-speed air will push anything in its path. Atmospheric pressure effects from the air include notable weather patterns around the globe, different pressure depending on elevation, and effects on living organisms who have adapted to certain pressure levels. So we can feel the change in pressure when we're changing elevation when our ears pop, because there's imbalance of pressure on the inside of our eardrum versus the outside of our eardrum. This fish, you might have seen a picture of this fish before. It actually looks like a normal fish when it's at the pressure level it's supposed to be underwater. All right, gas laws. No, we're not learning about the legality of where it is okay to fart. We are learning about the scientific and mathematical laws of how gases behave. We're going to look at 3 gas laws. So first one is Boyles Law. Boyles Law talks about the pressure and volume relationship for gases. They're actually inversely related. If you increase your pressure, you're going to decrease your volume. If you increase your volume, you'll decrease your pressure. So let's look at some examples. Right here, so our temperature is going to stay the same. Our volume here is 1 liter, so it's quite large, and we have a pressure of 1 atmosphere. We've increased the pressure to 2 atmospheres, but by doing so, we've decreased the volume. And over here, we've increased the pressure all the way up to 4 atmospheres, and inversely, we have decreased the volume. So, what happens to a balloon if you fill it in Denver and then take it up to Pikes Peak? What do you guys think is going to happen? It will expand. Whee! Why? Because Boyle's Law states that if you decrease pressure, volume will increase. All right, next is Charles' Law. So Charles' Law talks about volume and temperature, and they are linearly related. If you increase volume, temperature will also increase. If you decrease volume, temperature will also decrease, and vice versa. So, what do you think will happen to a balloon if you fill it inside and then take it outside when it's colder? It will shrink. Whee! Why? Because Charles' Law states that when you decrease temperature, you will also decrease volume. All right, but the big star of the show is going to be the ideal gas law, where it includes pressure, volume, temperature, and molarity. We're going to use something called a universal gas constant for all of our equations. So these are the acronyms you need to know. In order to use the ideal gas law, you need to know all but one variable in the equation. So say we need to solve for pressure. We would need to know the volume, we would need to know the moles, we would need to know our constant, and we would need to know temperature in kelvins. So we can rearrange the equation to look like this. P equals nRT divided by V. If we need to solve for volume, it can look like that. If we need to solve for temperature, we'll rearrange it to look like that. If we need to solve for moles, we can rearrange it to look like that. Awesome. So let's look at a couple examples. Here, a 2.5 mole sample of nitrogen gas has a volume of 5.5 liters at a temperature of 300 Kelvin. Let's calculate the pressure. So we give our knowns. We're going to put it in our calculator like that. And this is the answer we get. Let's do another one. So what is the mass of nitrogen in a 2.3 liter container at 1.2 atmospheres and 298 Kelvin? Here we need to solve for moles, our mass. So N is what we're solving for. So we know volume, we know pressure, we know temperature, we know our constant, and we know N. Oops. We're going to punch it in our calculator just like the equation here, and that's the answer we should get. Awesome. So, thank you for watching the gas video. Hope you enjoyed it. Hope you learned something. If you have any questions, please feel free to email me. All right. Thank you. Bye.